Hi, and welcome to 8.3 Kinetic Energy. In this lesson, students will be able to describe and calculate kinetic energy, and students will be able to describe the work kinetic energy theorem. So let's start talking about energy. We've been dancing around it by talking about what work is. We've done calculations to calculate how much work we're doing. Well, in order to do that work, you need to have energy. So it says energy is the capacity of a physical system to perform work. Energy exists in several forms. Energy is a scalar quantity. What do you think the units for energy should be? Pause the video, think about it. We're going to use joules as the unit for energy because we use joules for the unit for work. And it says, according to the law of conservation of energy, the total energy of a system remains constant, although energy may transform into another form. And it says a physical system, so that's part of the definition in the law of conservation of energy. It talks about a system. A physical system is a portion of the physical universe chosen for analysis. Everything outside of the system is known as the environment. The environment is ignored except for its effects on itself. So we're trying to break down different instances and just look at different objects and isolate them from everything else in the universe. That helps to make our calculations a little bit simpler when you're talking about energy transfer. So the idea for the remainder of this unit is we're building up to be able to do these law of conservation of energy problems. But before we know how to do that, we need to know the different types of energy because they're going to transform from one type to another. So this lesson is about kinetic energy. The next lesson will be about gravitational potential energy, and then we'll do elastic potential energy. And those will be like tools that we have that we can then use. The energy transforms from one form to another. And we're going to have these law of conservation of energy problems that we're going to be able to figure out because we know all the different types that we're going to learn about in this class. There are other types beyond what we learn about here. So it says energy is neither created nor destroyed. It simply changes form. So here are the ones that we talk about. In mechanical energy, you have kinetic energy, which we'll use as KE to abbreviate. Gravitational potential energy. Now in your reference table has it as delta PE, okay, the change in the potential energy. Sometimes I'll go GPE for gravitational potential energy. I think that kind of abbreviation makes sense, especially when we have elastic potential energy. Now in your reference table, they do a little different. They do PE subscript S, and the S stands for spring. So elastic springs, we'll get into all that. It doesn't have to be a spring, but that's what they use here. That's kind of why I prefer elastic potential energy to be abbreviated like EPE, but that's not how the rest of the physics world does it. But I just use these two to help explain and differentiate between the two. So there's also non-mechanical energy, which includes internal energy or heat. Now we talked about this very briefly. Do you remember the unit? Where did we see internal energy before? What causes heat or internal energy in most cases? We learned this in Unit 5 when we talked about friction. So, and you also learned, you've seen this cube before in chemistry. That's what they're talking about with heat. So that's a type of non-mechanical energy. You also have electrical energy. We're going to be talking about this in Unit 11 when we do electricity. That is not in the mechanics unit. We're still in this since the beginning of the year, we've been in the unit mechanics. Eventually, it's on the horizon. We're going to shift out of mechanics and go into electromagnetism, which has to do with current in wires and electrical energy. Chemical energy is something that we don't talk about in this class, but it's good to know exists, and it's the type of non-mechanical energy. And nuclear energy we talk about on like the very last lesson in the modern physics unit. We don't really do it justice in this class. You could take a whole course on nuclear energy, but it is interesting stuff, and we try to teach the very basics of it later on. So, starting with kinetic energy, the energy of an object that is due to the object's motion. So there's going to be a check. You're going to be given a word problem, and you have to check, oh, what type of energy is present here? Is it kinetic, gravitational potential, elastic potential? What type of energy is present in this random word problem? So there's a check. If something is moving, it has kinetic energy. If it's at rest, it has zero kinetic energy. Okay, but even an airplane in the air, yeah, there's gravitational potential energy there because it's high above the ground, but it's also moving. So it doesn't have to be one or the other. You could have both. The units, luckily, are joules, so still energy, still joules. And this is what the equation looks like. Ke is equal to 1/2 mv squared. It depends on the mass. If you have more mass, you're going to have more kinetic energy. And it really also depends on the velocity. The velocity is being squared, so you need to be moving. If the object's moving, it has kinetic energy. Remember, kinetic energy is a type of mechanical energy, okay? When we do the law of conservation of energy problems later on, they're going to say what happens to the total mechanical energy of the system, all right? And if energy is conserved and there's no outside forces happening, the total mechanical energy remains the same. It can transform from kinetic to gravitational potential. It can transform, but the total mechanical energy remains the same as long as there's no external forces acting on the system. So that's a concept to remember. And what happens a lot is kids see, okay, I have an equation for kinetic energy, an equation for gravitational potential energy. There's all these different equations for each type of energy. Then I throw them a oh, what happens to the mechanical energy? And they say, Mr. Nangle, you never taught me an equation for mechanical energy, because they forget that previous slide that was just up there. Remember, kinetic energy, gravitational potential energy, elastic potential energy, they're all types of mechanical energy. You're not going to get an equation for mechanical energy because it's an umbrella term. So where is the formula for kinetic energy? You guessed it. It's on the back page. Again, we're in the mechanics unit still. There's a lot of different concepts in the mechanics unit, and we are towards the bottom right over here, 1/2 mv squared. That's the kinetic energy. And don't forget, on the right-hand side, in alphabetical order, they have everything you could possibly want from those equations. So let's do a quick example. Should be pretty simple. A block has a mass of 20 kilograms and is being pushed at a constant speed of 5 meters per second. How much kinetic energy does the block have? So we are going to write down the given information. The mass is 20 kilograms. The velocity or speed is 5 meters per second. What is the kinetic energy? Pretty easy, right? We just learned this equation. Big surprise, we're going to use it now. 1/2 mv squared. So you just plug in the numbers and you solve. Don't forget to square the velocity. The kinetic energy is equal to 250. What are the units for kinetic energy? Do you know? Do you remember? It's joules. Any type of energy is going to be measured in joules, including work. Work is measured in joules. Do a lot of work, you could buy a lot of joules. Okay, so just really quick, we're doing some relationship problems. There's going to be a graph that pops up on the screen. It says, what is the relationship between the kinetic energy and the mass of an object? So you could have a little smart car like that, or a huge tank. If you increase the mass, what happens to the kinetic energy of the object? Well, you can see from the equation, it's a direct relationship. If I double the mass, the kinetic energy gets doubled. Direct relationship, just like this, okay? So more mass, more kinetic energy. And we could do the same thing with velocity. What is the relationship between the kinetic energy and velocity? So it's a slowly moving car or a really fast one. What happens when you increase the velocity? What happens to the kinetic energy? What does that graph look like? If you want, you could pause the video, think about it. It's actually an exponential relationship because this velocity term is being squared. So if I double the velocity, it's 4 times as much, 2 squared. kinetic energy. And if I triple the velocity, it's 9 times as much, 3 squared. So that's where we get this exponential relationship from. So we can do a little bit more with this. We're going to derive the work kinetic energy theorem. It says a 5 kilogram block is initially at rest on a horizontal frictionless surface. A 5 Newton force acts on the block over a distance of 5 meters. What is the final velocity of the block? This should look very similar to the do now that we did. And we used Newton's second law and a kinematic equation in 2 steps to do that. But instead, we can derive this new work kinetic energy theorem. So we are doing work. We are doing a force times a distance, 5 newtons over 5 meters. Well, what did we know about force? If you're looking at the net force, we said that we will use Newton's second law. So let's solve for F. What is F equal to in that equation? It's equal to ma, ma. So you replace F with ma in our work equation, and we get mad, but don't get mad, get glad, because when you get mad, all you have to do is look at the add. So AD, where have we seen AD before? This is going to be a weird one, but it's the kinematic equation that we used in that do now. And if you solve for AD, what you get? You get 1/2 VF squared minus VI squared. See, because you divide both sides by 2. Dividing by 2 is the same as multiplying by 1/2. Ooh, do you see the writing on the wall? Where is this going here? Okay, well, we're going to plug in this every time we see an AD. So this goes into that, okay, and transforms into that. And now this looks pretty messy. What is this work? We still have the work equation here. We're just manipulating it. What is the work equal to? Now let's clean this up and let's distribute the 1/2 and the m to both terms in the parentheses. And what does that look like? It's 1/2 mv squared. So this is the kinetic energy formula. This is the final velocity, so it's the final kinetic energy. And this term is the initial velocity, so this would be the initial kinetic energy. And we can rewrite it just like that, the final kinetic energy minus the initial kinetic energy. So what is that? This is the change in the kinetic energy. The change in the kinetic energy is equal to the work that you do on the system. You can either speed the thing up by doing positive work, or your final kinetic energy might be less than your initial kinetic energy. You're doing negative work on the system and slowing the object down. That is the work kinetic energy theorem. The work is equal to the change in the kinetic energy. And this is also where that equation comes from. We kind of took it at face value, but this is showing it's a combination of Newton's second law and one of the kinematic equations that we derived in Unit 2. So here it is, the net work on an object equals its change in kinetic energy. The work kinetic energy theorem. Let's prove it by doing a little example here. And if you want, you could try this on your own. Pause the video, read the question, and then see if you got the answer right. So it says a 100 kilogram block initially traveling with a velocity of 2 meters per second. So it does have some initial kinetic energy already, but it's going to be accelerated by a net force of 50 newtons over a distance of 10 meters. Okay, so I see a force over a distance. We're doing work, and it's accelerating. That means it's gaining some velocity. The work that we're doing is equal to that gain in kinetic energy. So we're going to just like kind of piecemeal it. And even though we just derived the formula, we'll see, does it really work out the way it should? So part A says how much work is done on the block. And then part B says what is the change in the kinetic energy? So if you calculate that change in kinetic energy, it should be the same as part A. So does the work equal the change in the kinetic energy? And then we break it down for, oh, how do I actually calculate the change in the kinetic energy? All right, but this is really just proving the theorem. If you wanted to, you could use the theorem like we did for the do now problem. You could just use that theorem instead of doing the two steps with the Newton's second law and the kinematic equation. So how much work is being done on the object? So part A, all right, we can, should we write down all the givens and the unknowns? I guess we should. Okay, so we want to make sure we don't get points off for not writing our units. So the part A says, what is the work being done? And then we're actually going to calculate what the initial kinetic energy is, what the final velocity is, so that we could know what the final kinetic energy is. We'll calculate that after, and then we'll just subtract the two kinetic energies to see what the change in the kinetic energy is equal to, and the work should be equal to the change in the kinetic energy. So that's the roadmap of what we're going to do. If you want to pause the video now and try it on your own, I highly recommend it. So part A, pretty straightforward. It's what we've been doing. W is equal to FD. The force is 50 newtons. The distance is 10 meters. So we are doing 500. What is the unit for work? Joules. 500 joules of work is being done on the system. And the force is parallel and in the same direction as our displacement. So that means it's going to be positive work. We're adding 500 joules to the system, and we would expect the change in the kinetic energy to be 500 joules. We're adding that energy to the system, so that's what the change in the kinetic energy is equal to. Kind of nice how that works out, right? So let's see if that's really true. So that's part A. Part B says, find the kinetic energy. So the initial kinetic energy is equal to 1/2 mv squared, 1/2 100 kilograms times your initial velocity of 2 meters per second. Don't forget to square it. Your initial kinetic energy is equal to 200 joules. Okay, that's nice. So this is part BI. If you want, I could do like that, and then BII. B.II says calculate the final velocity. Use Newton's second law and the kinematic equation. This is like multi-step like we did on the do now. So we're looking for the acceleration first. It's equal to the force divided by the mass. If we know what the acceleration is, we can use a kinematic equation. So the force is 50 newtons, the mass is 100 kilograms. Your acceleration is 0.5 newtons per kilogram, or meters per second squared we would use, right? Because we're talking kinematics right now. So we know the acceleration, we know the initial velocity, we know the distance. We're looking for the final velocity. So which equation should you use? I'll write it out as like a sub thing. All right, so you want the equation without t in it, and it's the equation that we used before. So Vf squared is equal to Vi squared plus 2AD. You'll substitute in your numbers, and then you solve for Vf. You end up doing the square root of 14, which is 3.74, 17. We'll keep it long because we're going to use this number, and we want to try to get 500 joules. So the longer the decimal, the closer approximation we have, which is good. So for part 3, BIII, okay, it says calculate the final kinetic energy and then the change in the kinetic energy. All right, so we're going to do the kinetic energy formula. Then you substitute in and try to use this long decimal in your calculator if you can. Actually, since we're squaring it and this was the square root of 14, this just turns into 14. So it's 14 times 100 times 1/2. The final kinetic energy is equal to 700 joules. Oh, Mr. Nang, I thought it was supposed to be 500 joules. Well, you want the change in the kinetic energy. We had 200 initially. It was moving already. You had some kinetic energy. Now you have more kinetic energy. Where did you get that kinetic energy from? The work. Because what are we going to do? We're going to do the change in the kinetic energy is equal to always final minus initial when you're doing change. Oh, that's an equal sign, minus. You can already see what it is. Delta KE, right, is equal to 700 minus 200. Wow, look at that. The change in the kinetic energy is equal to 500 joules. Nice. So that's equal to the work. So I'm going to erase this all now and show you how you could have done this problem in one step, in one equation using the work kinetic energy theorem. So if we know that the work is equal to the change in the kinetic energy, then we know that the work is equal to the force times the distance. The change in the kinetic energy is just the final minus the initial. So, and by the way, you probably want to do FD cosine theta because that'll give you the right sign. Are we doing positive work or negative work? Right now, the angle between the force and the distance is 0, so it gives us positive 1 when we do cosine of 0. But that'll help you with this because we got 1/2 mvf squared minus 1/2 mvi squared, okay? And at this point, we know, let's do the checklist. Do we know the force? Yes. Do we know the distance? Yes. Do we know the angle? Yeah, we said it was 0 degrees. Do we know the mass? Yes. Do we know the final velocity? No. Do we know the mass? Yes. Do we know the initial velocity? Yes. So this is actually one equation that you can use to find the final velocity instead of having to do, the Newton's second law and then the kinematic equation separately. Plus, you get the added benefit of having the work in there as well. So in case they were saying like, oh, how much force were you exerting? Or over what distance did this change in the kinetic energy take place? You could use this equation to solve for all of those different things, which is kind of nice. Just like that. All right, so that's about it. Thanks for watching and have a great day.